Good day, ladies and gentlemen, and all the viewers at home. Today I will going to be presenting on one-dimensional hydraulic flood modeling simulation using HEC-RAS. The problem come from the research done by J.S. Beck and G.R. Basson. But I'm just going to present on the work that I've done on this particular scenario. This scenario is based on the Pongola River. Then the scope of work that I'm going to present the results on will be on the following. I'm going to do one-dimensional hydraulic modeling simulation on the Pongola River Ridge from the left and right bank stations with consecutive cross sections which are 0.5 kilometer apart and contraction expansion coefficient being 0.1 and 0.3 respectively. And the subcritical flow that I'm going to be used will be 3,200 meter cubed per second. Secondly, I'm going to redo the hydraulic flood simulation with flows that occurs in 300 years, one, and the two twice in 100 years respectively. Starting from the upper section, which is the most upstream section, and then using table 2 as the basis. Now, when you look at table 2, it is giving us the return period for 20 years. The peak flow is 4,150. And for return of 50 years, 9,250. And 100 years, 1,250. And the return period of 150 years is 14,550. So we are going to either interpolate or extrapolate or maneuver a way on how to get the return period as defined. And the last task that we're going to do is to redo the simulation if the meaning coefficients values have increased by 60% and 90% respectively for all cross section. Now if we move to the next, now the HEC-RAS as a program was developed using the Manning's equation, which is Q, K over N, A, which is the area, R to the power of 2 over 3, which is hydraulic radius, and S to the exponent of 0.5, which is the overall slope of the river channel. So what we are going to do actually is to look at the mathematical relationship between all these parameters. What happens when you change the Q? But you change the Q, more or less all the parameters remains the same. Or what happens when you change the parameter N and everything else remains the same? You are going to check the N against the Q, because the Q is the one that will give us the relationship of the flow and what happens to the flow level, which on the graph we're going to show is the elevation. Or that elevation can also emanate from the parameter AR 2 to the squared, which will define the elevation. We'll just check what happens when we vary the parameters. That is what is going to give us the results that we are expecting. So we know the S we said is 0.001. Then the A and R, it will depend on the flow. And the Q, if we set the Q as fixed, we check what happens here between A and R, which would give us the elevation. But now, yeah, if Q remains the same, we change the n. What happens to this a and r? That is what we are going to basically check. Q against a and r, n against a and r. So that parameter will be the elevation, and then we'll just check what happens to them, if whether the mathematical relationship here do make sense. Yeah, but by merely looking, the Q seems to be in direct proposition with a and r squared, if everything remains the same. But now we'll check what happens with the parameter n. Looking at this equation, it seems as if it's a denominator. But now, what happens when n, the parameter n itself, is a fraction? And then now you are changing the denominator of the fraction. So what happens mathematically? That gives you the direct proportion. But you're going to look at the results. Now, after running the simulation, these are the results that you get when the Q, which is your discharge, is 3,200 meter cubed. As you can see there, the value is just below 90, roughly 85, 87. And it goes above 90, which could be 91 or 92. And the energy level, but you're not going to focus much on the energy projection. We're just going to check the flow. What happens? This is the flow when the Q is 32. So we are now 32,000, sorry. So we are going to compare it to what happens when we vary the Q, when we increase it, with the period that with the frequency that is given our t, where they say it is happening twice in 3 years. So it means it's going to be 2 over 300, which will give us the frequency of 1 in 150. So we shown the table there on what is the value. Now, looking at this slide, this is what you get. I tried to make sure that the two slides that I'm comparing are as congruent as possible so that we can see the difference. So on the first component is when the Q, which shows our discharge, the flow, is 3,200 meter cubed per second. Now you can see the level of flow where it is now. It is between 0 and 90, which is roughly 85 meter cube, meters in terms of the elevation. Now what happens when the Q is 14,550? Look at that. Look at the level. You have higher elevation. And higher elevation means higher energy. Then the flow is too much. When the flow is too much, there is a rise in elevation. There is a rise in elevation. Now we get to the second parameter that we are required to look into, which said, now this is happening twice in 100 years. 2 over 100, 1 over 50. That will be a frequency. So now we compare the discharge of 3,200 and 9,250. You can see here, this original, we use this 3,200 as the baseline. I tried to make them as congruent as possible so that they start from the same point, which is the point between 90 and 80, roughly 85, 87. And then now look at that, the level is still higher. But now if you compare the previous one, the level is in between the highest, which was 14,550, 920 now, is in between. It's in between. So which is in line with what is expected of us from the mathematical relationship. So now we can see that whenever you increase the Q, which is our discharge, the elevation level increases. But what this tells us is that there is a direct proportionality. We can say it's linear in a sense, because now we increased from 3,000 to 9,250. It's roughly 700 meter cube, no, 7,000 meter cubed variation as compared to the 14,550, which is roughly 11,000 increase, which is much more higher than this one. So at least the simulation seems to be agreeing with the mathematical principle. Now we come to the point where we increase the parameter n, which is a rough coefficient, the rough coefficient of the stream. Now the first parameter where we checked the 3,200 is the n was 0,019 and 0,025 for the left and the right embankment. Now we increased it by 60% and 90%. So the new n is 0,0405 and 0,0361. But now we had to keep the Q, which is the discharge, at 3,200. We could have done it with the new Qs that we found, the 9,250 or 14,550. I think the results will still be the same. Now look at what is happening. The level, we try to make it as congruent or similar as possible. Now the starting level is between 0 and 90. Now look at the level of flow, the elevation, the change in elevation. So it means when you increase the rough, the rough surface, the surface roughness, which is the parameter n, it increases the elevation. The elevation is the flow level. So now we see it here that the flow level has increased. When you look at it, you look at it at the elevation. So the detailed report is provided, but we are just showing you what changes when you change the parameter. I think I've given the results that were required. That in overall we can say when you increase the discharge, which is Q, the elevation increase. The elevation increase. That speaks to the flow of water. The flow of water increases. The velocity increases. So that's what happens when you change the Q. But now we see even when you change the N, and then the discharge remains the same, it means there's also an increase in the surface, the water surface elevation. And that will result in higher energy. That will result in higher energy. Thank you, ladies and gentlemen. Thanks you for your time. I hope you enjoyed the video. Thank you.